Today we will solve a problem called word ladder, and this is the second version of this problem. So feel free to check the first version also. So here we have a number of words in a list, and we have to reach from word 1, which will be called the starting word, and then end word. So we have to reach from here to here, and there can be multiple paths. So it's not really a ladder, it's like a graph, and there can be multiple paths. So the paths have a length. So if we have multiple cities, let's take some practical example. City A, B, C, D, and we have to go from city A to D. Then maybe we need to go like A to B, B to C, then C to D. So this path has a length of 3. But maybe there are a few more paths, A to C, C to D. So this path will be 2 length. And next, let's say A to B and B to D. This will be also of length 2. So there are 2 paths of length 2 and 1 path of length 3. So we are interested in the shortest one. And there are multiple such paths. So we have to return the list of all those paths. So here instead of cities, we have words, and we have to transform one word to another. And let's see some rules. So if we have a word, let's say ABC, just 3 characters in this word, then from this word I can go to either AB and some wild character here, I'm writing asterisk, or maybe A asterisk C or asterisk B C, and this asterisk can again take multiple values. So here the meaning is that just one character in the word is changing. So from ABC we can go to ABD, ABE, ABF. So just one character change is fine. Similarly ACC, ADC, and so on. So you get the idea. So we are allowed to go to a word W1 to W2 where there is a change of just one character. And this word W2 will be called adjacent to W1 because there is a path between these two, and these two will be said to be connected. So in a graph we have notion of connected nodes. So we can only go to connected nodes. So if 1, 2, 3, 4 is there, from 1 we cannot go directly to 4. We have to go via 2. So from any node we can only visit its neighbors or adjacent nodes, and in the terms of words this is what it means. So now let's come to the problem. So we have one starting word. So this is the starting word that I was talking about. This is the destination which we have to make, and it can contain a sequence of words. So words means nodes, so it will denote a path. So hit, from hit we cannot go to dot, because if you compare hit and dot, you see that T matches, but this first character does not match, second character does not match. So there is a difference of 2, but we can have a difference of at max 1. And these words, the neighbors, have to come from this list. So these are all the nodes of the graph, or here in this problem it's the list of words. So starting is hit, that is fixed. Ending is cog, that is also fixed. So we have to reach from hit to cog. So from hit, which node we can take? If there is no node which we can take, then we will return an empty result. There is no path. So in the graph terms, if this is a graph and this is the starting node S, and there are a few other nodes, and these are connected among themselves, and let's say this is destination, but S is not connected to any of those, so no path exists from S to T. Similarly, if no such word exists in this list, then straight away return this empty list. Also here the adjacent word should be of the same length. So it's not that ABC is a word and then AB is a word. So we can go here because this is just one character difference. No, the length should be same, only the value can be different. So this we have to keep in mind. And it's given that you don't have to worry about this length difference, that will not be in the input. So from hit we can go to hot, because there is hit, hot. So the difference is just here, all the two words are same. So we can go to hot. From hot, can we go to any other word from hit? No. Dot, no. Dog, no. No other word. From hot we can go to dot is one, because there is just one character change, and lot is another one. So you see a graph is forming, lot, and any other? No. From dot we can go to dog, and no other word. From lot we can go to log. From dog we can go to cog, and from log also we can go to cog, and this is the final word, so we don't need to check further. If we go further and maybe there is another path, that will be longer. So if even if from log there is some other word, let's say tog, and from tog there is cog, so this path will be longer. So we will stop once we process this. So let's draw the graph from this. So hit is there, let's draw the nodes. Hit, hot, dot, dog, then we have lot, then we have log, cog. Now hit is connected to hot, so there is a edge between these two. Hot is connected to lot and dot, then dot is connected to hot and lot, and similarly log is connected to dog and cog, and dog is connected to cog, and log is connected to lot. So this is the graph we are talking about. So starting node is given, so this white node is the starting one, and this is the final node, source and destination. So this is a simple graph problem. We have to find the shortest path from source to destination, and there can be multiple paths of the same length, same as the shortest one. So we have to find all such paths. So from S we go to hot. From hot we can go to either dot or lot, both. So you see we are proceeding in breadth first search manner. So we start from a source, we go to all the neighbors. So just one neighbor, so we come to hot. From hot there are two adjacent neighbors, dot and lot. So these two comes next. So let me redraw here. So we have hit. From hit we can go to hot. From hot we can go to lot and dot. If there would have been any other adjacent node, we would have visited that also, because this is the first node in the path, the result. This is the second node. These two are candidate third nodes, and we don't know, maybe from one of these we don't reach the destination, so we will not include that. But these three are all equidistant from this, so we are visiting in breadth first search manner. This node, then its neighbors, all the neighbors that are 1 unit distance from here, then all the next neighbors. This is level 0, level 1, level 2, and so on. And let's say destination was here, and there are multiple paths leading to this at level 4. So shortest path will be of length 4, and there are multiple of those, so we don't need to check further below this. So this is what we are doing. So this is clearly a breadth first search. So if you are not familiar with breadth first search, I would recommend to check my video on breadth first search before coming to this, because you can understand it, but while writing the code you may get stuck. So the idea is that we push the source to the queue. So this node is visited, the source here. Then we see all its neighbors and we push all of them to the queue. So we pop this node from the queue and then push all its neighbors. So at any point of time, so these 3 nodes are in the queue. These 3 nodes are at level 1. Now we take a counter that 3 nodes are there. So we run a loop for I equal to 0 to 2. Keep popping them and keep pushing the neighbors to the queue. So these white ones will be pushed after these yellow ones, irrespective of whether they are neighbor of this one, this second one, or third one. But we have already taken the count. What was the count before we started processing the next level? That was 3. So for the next 3, we know that we are processing the earlier level. Now when this loop ends, these all 3 will be popped from the queue and only level 2 nodes will be there in the queue. Again, we will take the count and then keep pushing that so that elements are traversed in level by level in order. So this is the essence of breadth first search in short. Now here we are doing the same thing, and then from lot, so dot and lot and dog and log. And then we have cog and cog, and this is essentially the 2 paths. So we have to return here hit hot lot log cog. This is 1, and hit hot dot cog. So a list of lists. So this is what we have to return. So how we are doing? Let's start again. So we have initially a list of words which contains so this it's given that this initial word or the end word may or may not be in this list. It may be or it may not be. So we will create an exhaustive list where we include all the words, or we can skip the first one because this will be the first word that will go into the queue. So no need to insert and then pop back again. But we can do that for completeness. So let's create a bigger list. So hit hot dog lot cog and 2 4 5 and then we have log and dot. So this is the exhaustive list. So we will keep them all in a hash set or unordered set in C++, because we will be need to check access or find some words. So we can keep them in a set, and then what we will do, we will pull out the first word and put it into the queue. So now queue contains hit, and in the queue we keep track of the running path. So when we are at hit, we are denoting all the paths starting with whose first word is hit. We are extending this path until the last node is cog. So this is a running path we are maintaining, all candidates running paths. So till here it was hit, then when we reach here we have hit and hot. So all the paths have to start with these 2 words only. This is the only path. Now here we have 2 paths. So this will fork 2 different paths that we need to keep track. So after this level, when we reach this level, we will have 2 paths, hit hot and lot, and also hit hot and dot. These 2 are running paths, path 1, path 2. So we have to process this entire thing, and we will we need to extend this path. So when we are extending it, we are only interested in the last word, because this path is already built. And what next word can come here? So we have w1, w2, w3 in a path p, and we are looking for what is the next word that can come here. So we will only be comparing the last word in this running path and check what are the neighbors of this w3, and we will append all of those. So let's say first word is w3x, second word is w3y, third word is w3z. These three all are neighbors of w3. So this path will result in 3 more paths. And we have to process all of these. Maybe some of these lead to the target, some of these does not lead. So whichever leads to the target, that will be part of the answer. So you see, we are keeping track of a running path. This you have to keep in mind while writing the code. And we are extending the path based on the last word, so that it forms a sequence, w1 to w2, w2 to w3, and so on. So initially hit is there in the queue, then we write a simple BFS code while not queue.empty. So till the queue is not empty, keep doing it. So we have path which pop it from the front. So get the front and also pop it. So now hit is removed. So this path is denoting hit, and this is not the complete path, it's the incomplete running path. So currently it has just one word, but this will get extended. Now we pick the front and we see what are its neighbors. The same thing we do in normal BFS. We pop a node and then look for all its neighbors. So we will better to define a function find neighbors in the code, and we will pass a word and this word list, and this will return a list of all the neighbors. Or you can write here also, but better to create a separate function. So this find neighbors will return, so its neighbors are hot and nothing else, just one. So we will append, if this has multiple words, then just see here. So hit hot has 2 neighbors, lot and dot. So this path will fork into multiple paths, the same as number of neighbors. So currently it has just one. So the new path will be hit and hot, and this will be pushed to the queue. So now queue has hit and hot. Now again queue is not empty, so we will pop this one. So now path contains hit hot, and this is popped, so this one is gone. Next, this is the path, so we only check the neighbors of last word. We are not bothered about this. This is already a semi path. So what are the neighbors of hot? Those are the candidates which can come here. So again we will call find neighbors. It will return hot has neighbors lot. So these are neighbors, lot and dot. So 2 neighbors this time. So we will have 2 new paths. So we will insert all of these 2 in the queue again. So queue is here empty, but we have not went till the end of this while loop. So before reaching here, again these 2 will be pushed in the queue. So the new paths will be hit hot, then lot. So this will be pushed to the queue here, and hit hot dot. This will also be pushed. Now the queue has 2 paths, hit hot lot and hit hot dot. These two are in the queue. So again, queue is not empty. So this we will first remove the first path. So P is hit hot lot. Then we will find the neighbors of lot, which are dot and log. Dot and log. But dot we have already here. So when we process a label, we also remove all the nodes which we just processed. So here when we included this lot and dot into it, and we are now ready to go back to the beginning of this loop. Before that, remove this lot and dot from this list. So dot and lot removed. Similarly, in the beginning, hit was removed. Next, hot was removed, so that we don't reach to that node again in the next level. So it's okay that it's okay to be like this. So this is node 1, node 2, node 3, node 4, node 5, and let's say this is also connected. So it's okay to have reach this node 4. So we can reach this node 4 from multiple nodes in a previous level. So once we process this, we have to remove this 4. Once we have processed both, otherwise if we just process 2 and remove 4, then we will never find this edge. So once you process all the nodes in a given level, you remove all the nodes which we just visited. So we will have a visited array also, which we will remove from the list. So that next time, now 4 is gone. So in the next level, when we reach 5, we will not include this edge, because from 1 to 4, there are 2 paths of length 2. So there is no point in reaching 4 with 3 edges. That will never be the shortest. Maybe from 4 we are reaching the target. So this path, the white one, this is 5, let's say. So 1, 2, 4, 5. This is a path of length 3. Similarly 1, 3, 4, 5. But if we allow this edge also here, this one, then the path will be 1, 3, 5, 4, maybe make it 6. This length is bigger, so that's why we are not bothered about this length. So as soon as we process all the nodes in a given level, remove all the visited nodes from the list, so that these are never discovered again. These are already visited. Now so dot will not be included here, since we would have removed this dot after third level or second level. So dot will not be here. So log will be here. Just one neighbor, and the next we will pop this one, the second path. So it will be hit hot dot and then dog. So now these two are removed from the queue. So queue is now again empty, and now we have processed again a new label. So we will remove which words? Log and dog from the list. So this list, dog and log, are removed. Now in this list just cog remains. Now again these two are in the queue. So the queue has hit, hot, lot, log, and hit, hot, dot, dog. These two paths are in the queue. So again the queue is not empty, and we have also not reached the end word. So you will see that we will later keep track of whether we have reached the target word or not using just a boolean flag. Now we pop the front element. So path is hit, hot, lot, log. So what are the neighbors of log? We will search in this list. So we will find cog, just one neighbor. So we will append just one neighbor and push it to the queue. And next one, and also since this is equal to the destination, we can now be sure that next level we don't have to process. This is the last level we are processing. So this is removed from queue. Next, this one is popped, hit, hot, lot, dog. Next we find neighbors of dog, which will be cog. So you see why we are not removing this in between. We remove the nodes only after we process all the nodes at a given level, because there can be the same thing, multiple paths from previous level to a given node. If we remove after visiting this first one, we will never discover the second one. So again it will find a neighbor, just one neighbor, cog. So we will just append cog. And again we will add this. So as soon as we reach a destination, the last word, we add this running path. This running path is now complete. So we will add it to result. Similarly, again here cog is reached. So again we push it to the result. So in this case, two paths will be there. So you get the idea. Now, once you are comfortable with this reasoning, why this is so, we are ready to start the code. So let's implement our logic. So you can go through a few more examples. So in this case, the path is empty. There was no path from hit. There is no neighbor of hit here. Or a hot is neighbor. Then we can go to dot, then dog. Cog is not in the word list. Okay, so cog is not in the word list, therefore there is no valid transformation sequence. So if the last word is not there, then again it cannot be formed. And begin word does not need to be in the word list. Okay, so that should not affect anything what we have seen. Now we will need a function to find the neighbor. So first let's complete that. So that should return a list of neighbors or a list of words, and words are a string. So a vector of strings, find neighbors. So this should take the word and also this reference to the word list. So how do we find? One way is that you pick all the words in the word list one by one and start comparing. So that should also work. Another way is that using this logic. So what we were seeing here, this one. So we were saying that this asterisk character. So first we are replacing the first word with B, C, D. Try all the letters. So these are made of small English letters. So we can try replacing all of those and then match whether that word exists in this list or not. So we said that we will convert this to a set so that searching is easy. So instead of vector we can have unordered set of this one, and here we will create the unordered set. Otherwise searching in this vector will be one by one. So first we will replace the first letter with all the letters in English alphabet, smaller letters, then the second letter, third letter, and so on, and then we need to restore the word back. So that's why we are saving what was the earlier character. So what we are doing here, so we replaced first character with letter A. So this word, the new word, is different from the original word by just one character, and we then find whether it exists in the word list or not. If it exists, then it's neighbor, and if it does not exist, we do nothing. Then we replace the second character again by A to Z. We try all the combination, and again the third character in the word by all the combination, and then find in this hash set. And finally, when we are done with it, we restore that character back, otherwise the words will change. Now we have the function ready. We are ready to write the main function. So result is a vector of strings. Then we will need a queue. So this is the running path initially, just the begin word. All the paths will start with this node, and this will get extended and forked into multiple paths. Then reached end. This we have to keep track. When we reach end, we add that path to the result, and also we don't proceed further to the next level. And remember, we need to remove all the nodes. Once we have processed all the nodes at a given level, we will remove all the new words that we reached or included in the path. So this we will keep track in visited. Now the normal BFS thing, while not queue.empty. So this loop, so initially we find how many nodes are there in the queue. If it's, let's say, 5, then this loop will run 5 times, and it will also be pushing the neighbors back to the queue. So we will not be able to segregate which one was from which level, but before starting that, pushing any node from next level, we keep track of how many nodes are there in the queue. That's how we process all the nodes at a given level together. And then after this loop, this queue will only hold the nodes at the next level, and again we will find the size, and again. So this helps in processing the nodes level by level. So this is the path. We can write P for path, running path, which the same thing we used in the explanation. So this is the running path or prefix of the path, not the complete path. Then queue.pop, and then the neighbors of the last word here in this running path. Last word, path dot back, the last word, and then we need to pass the word list, not this vector but this set, so that this function is faster. If we find in the vector, again it will work, but it will take O of n time. Here it should take lesser time since it's a hash set. So these are the neighbors. So if there are 3 neighbors, we will append all the 3 words to this path. So this path will grow and it will break into 3 more paths. But if there is just one neighbor, then the number of paths will remain same. So so we have to append all the neighbors, all the words in this list at the end of this path, and then push them all to the queue. So vector string new path, so this is the current path. You can write current path or just path. So here it's just a copy of this path. Then we have to append. and we also have to push it to the queue. And so this neighbor was included, this neighbor j was newly included in this running path. So once we are finished with all the nodes in this level, we will remove it from the original list, and this is which we keep track in this widget. And this is unordered set, so it will not allow duplicates. If a node is reached from multiple nodes, this will be inserted only once. You cannot remove more than once anything from a list. So widgeted dot insert this neighbors j. And one more thing we need to keep track of, maybe this neighbors j was the target word or the end word. Then if we don't keep track of that, if we don't compare that, we will keep processing it till we reach the maximum level. So we have to also check whether that is the case or not. So if neighbors j is equal to end word, then this should be added to the result. So result dot push back this new path, and this is the complete path now. Also we will make this reached end equal to true, and once we process all the nodes at this level, we will check whether reached end is true or not. If it's true, break out of this while loop. So we are pretty much done here. We need to come here, so the ending bracket is here. And we need to remove these. So now we have removed the nodes that were just visited in the previous level, so that we don't reach there again with a longer path. And then visited also needs to be cleared, otherwise it will have unnecessarily hold elements which are already deleted. And finally we return the result. And let's see if it works. It's a long code, so don't get too worried if you get some compilation issues in the beginning. Push back new path. New path is a vector of a string, and result should not be this. You can see the return type it vector of a string. So vector of a string denote one path. It's a vector of those paths. Spelling mistake. Hit hot dot dog cog. Yeah, so it seems to be fine. And the solution is accepted here. So you can try in other languages also. It's a very long code. Writing in Python and Java again would take maybe 10-15 more minutes. So if you have any better solution, you can share your comments. Thank you.